Hi folks, welcome to another tutorial on Basys 3 board, and today we are going to create a calculator. So just to give you an overview, here is Basys 3 board. If you look at it, you got switches at the bottom and you got LEDs right above that. What we are doing in this project, we're actually going to make a basic calculator which will actually be able to add two 4-bit numbers, subtract, multiplication, and also division. And we are going to use LEDs to display the answer. So the first 4-bit number will be entered by the user using the switches. If you notice, this is SW0, this is switch 0, switch 1, switch 2, and switch 3. So that makes a 4-bit number. And then switch 4 to switch 7, those will make the second 4-bit number. So SW0 to SW7 will be our two 4-bit numbers, and then we are going to use SW8 and SW9 for the user to input whether those two 4-bit numbers needs to be added or subtracted or multiplied or divided. Okay, all right, so let's get started. I'm going to right click here. I already created a new project. If you don't know how to, then watch the video at the very end that will appear, and I think the title on that video is how to get started on Basys 3 board. Well, I'm gonna right click here and click add source, click next here, create file. I'm gonna name the file, say calculator. If you don't have any space or anything, I usually use underscore. Click OK, click finish here. We have inputs, which are switches, and we actually need how many of those? Well, we have switch 0 to switch 7 as inputs, two 4-bit numbers, and switch 8 and switch 9. So we need 10 switches. So this will actually be 9. Okay, and how many LEDs we would need? Well, if you look at the because it's a 4-bit number, so the highest we can get is 15, and if you do the multiplication, that will give you the highest number. So 15 times 15 is 225 actually. 15 times 15 is 225, and therefore we would need at least 8 LEDs. Okay, so we will choose 0 to 7. So here maybe I'm also gonna make sure one thing here. All right, yeah, LED, and then this is a bus, and I'm gonna have 8 LEDs, so it goes from 0 to 7. This is all pretty much what I need, and these are going to be output, so I need to make sure it's selected as output. Click OK. In my design source file should appear over here. It automatically does the topology for us. So here we are going to start our coding. Now I'm going to declare wires, my addition, subtraction, multiplication, division, my core operation as wire, and those could be because I had the LED as 8-bit, so the answer could be 8-bit. So I need 8 bits here for addition. And then I have wire, subtraction. I'm declaring them as wire is because the answer, like addition, subtraction, and multiplication, division, this will change as there's a change in the switches, okay, at the logic, at the input. So this is going to be multiplication, and this is going to be so again, if you're getting confused like why I got 8 bits over here, because the LED, which is the output, we are using LED to display the output, and because we are using 8 LEDs, we are actually gonna make sure that all the answers, like whether all the operation, whether it's addition, subtraction, it is declared as 8 bits. This has to match. So say if you were adding two 2-bit numbers, so the highest could be 4, so we could have done 4 would make a code of 100, so we could actually have 3 bits, 3 LEDs. So this will go from 0 to 2. Alright, now I'm going to use the assign function. We are doing basically data flow model. Okay, this is the data model. Assign addition equals to S2. So I'll go back to my SW0 to SW3 makes one 4-bit number, and also SW4 to SW7 makes another 4-bit number. SW7 to 4 to 0, adding 2 4-bit numbers. Okay. And then actually I'm gonna copy this whole thing 3 more times. This is going to be my for subtraction. The only thing I need to do is change the operator from plus to minus. Multiplication, I need to change this to semicolons at the end of each line, and this one is for the division, the last one. And this is going to be replaced with /. Alright, now I've taken care of all my operations. I just need to lit up the LEDs, so I need to get an expression for it. And before I get the expression for LED, I want to go to this Word file that I just created. Okay, remember we have switch 9 and switch 8, those are doing some operation. So if the user chooses those 2 switches to be set to 0, then our calculator will basically add the 2 4-bit numbers. And similarly, if the switch 9 and switch 8 are set to high, the basic calculator will basically divide the 2 numbers. Okay, so this is our truth table right here for our basic calculator, and using this truth table we are basically going to get an expression using the sum of products. Okay, alright, let's get started here. So SW here is 0, so we need an inverter here. 9 ending with switch 8, because it's 0, so there's going to be another inverter. Ending with addition. So I got the term for this one. Now I need to move on to this one. And what do we do with all these terms? We basically add them, and operator for add in Verilog is this vertical line. Now switch 9 is 0, means it's off, so ending with, this is 1, so this is going to be switch 8, then ending with subtraction. And then again I got this vertical line for powering it. I got switch 9 as 1, switch 9, then I got switch 8 as 0, so this has to be with multiplication. So multiplication here. And then I'm gonna move on to my last term, which is going to be this one, as switch 9 and switch 8 both set to high. So switch 9 and then with switch 8 with division. Alrighty, perfect. Now there's one thing that we need to check here, and that is if you look at our switch 9 and switch 8, those are 1-bit numbers, meaning they can only be 0 or 1 at one time, right? Whereas if you look at your addition, subtraction, multiplication, division, in our Verilog code we have declared them as arrays, and those are 8-bit numbers. So you can only add 2 8-bit numbers. You cannot add 1 8-bit number or 1 1-bit number. So we're gonna have to find a way to actually make this switch an 8-bit number. And so what we do is basically what we do here is, say if I write down as, I'm going to use this curly braces and then curly braces open again, and I close these curly braces right here. Now if I take this expression and put it down over here, which I have already done, I'm just going to make it 9 here. Okay. So what does this mean? This means basically we have an 8-bit number. What are those 8 bits now? So if you look at your schematic, SW8, SW9, 10, 11, 12, 13, 14, 15. These are your 8 bits. Okay. The user is only going to adjust these 2, and rest of these 6 are, we don't really care what are they, whether they are 0 or they are 1. Okay. So this, if you write it this way, this basically means a switch number 15 is 1, switch number 15, 16, 15, 14 is 1 also, 13 is 1, 12 is 1, 11 is 1, okay, 10 is 1, 9 is 1 because switch is 9. It's not inverted. Okay, say if this was inverted switch 9, so this would have been 0. Okay, but I'm gonna remove it. Switch 9 is going to be 1, and then switch 8 is going to be 1 also. Okay, so if you look at it, 1 2 3 4, and then I got 1 2 3 4, the one extra 1, so I'm gonna skip that. So switch 8, switch 9, switch 10, switch 11, switch 12, switch 13, switch 14, and switch 15. I started with 16, whereas I should have started with 15. So switch 15 here and switch 8 here. Okay. So alright, so and I'm gonna use this bracket here, and similarly I have to do it for all these switches. I have to make these switches 8-bit. So 8 and close it here. Addition is already 8-bit, so I don't have to do anything here. I have to make this switch 9 as an 8-bit. So I'm gonna use this again here. I need to make it another switch right here that I need to make 8-bit. And then semicolon here. So it's like my expression for LED is complete. So I'm actually gonna copy it from here and then paste it over here. Okay, so here it is. Okay, yeah. So, and that's pretty much it, folks. My code is complete. Again, I can just go through it real quick. We have switches as inputs, we have LEDs as outputs, we are declaring addition, multiplication, subtraction, all the 4 operations as wires, and those don't need to be 8-bit numbers, because with a 4-bit number, the highest number you can achieve is 15. So the 15 times 15 is 225. That's the upper cap or limit. So we need to make sure we have at least 8 LEDs so we can display 225. And these are the operations using the assign function. And here I'm also missing an assign function. Simply using the plus operator for addition, negative operator for subtraction, multiplication and division. And then here's the expression for the output, which we drew using this truth table right here. I'm actually going to save it and compile it, and while this takes place, I'll go back to how this expression is going to work. For the output expression, reading. Okay, all right. Okay, so while this is gonna, since it's gonna take a few seconds, let's go and check. I want to prove, I actually want to give you an example for one of the operation, which is going to be multiplication. Okay, say switch 9 is set to high and switch 8 is set to 0. That means it's going to do multiplication. So because switch 9 is 1, okay, how would I write it in 8-bit? Well, it's going to be all ones. Okay, now remember, these could be yeah, these are all going to be all ones. Okay, and if you look at 0, which is switch 8 is 0, so that means it's inverted. So switch number 8 is going to be 0, which is right here, and all the other switches are going to be 1. Okay, similarly, if I had this right here, switch 9 was set to 0, then I would have had this as 0. I'm not gonna do that. Okay, remember, this is switch 8, this is switch 9, 10, 11, 12, 13, 14, and goes all the way to 15. Now switch 8 is 0 and switch 9 is 1. If you look at this term in the expression, because switch 9 is 1, this would mean this is going to be 0 because it's an inverted, and because it's an AND gate, any of the input 0, this whole term is going to be 0. Okay, right, let's move on to this one. Again, switch 9 is inverted, and because switch 9 is 1, that would mean the invert of 1 will be 0, so this whole term will be 0. Okay, let's look at the last one. Because switch 8 is 0 and switch 8 is 0 here, so this whole term will be 0. But if you look at the multiplication term right here, switch 9 is 1, that's 1. Switch 8 is invert, so 0, and the invert of 0 would be 1. So this would make will give you the multiplication answer, which will be stored in LED. Okay. Now, I already told you how I got these numbers. Invert of switch 8 means switch 8 will be 0, rest of the other bits will be high. Switch of switch 9 would mean switch 9 will be 1, and rest of the other switches will be high. Say we have two numbers, user enters 0000100, which makes a binary code of 4, and then the second number the user inputs is 00000010, that makes a binary code of 2. Okay, so if you're doing a multiplication, 4 times 2 will actually give us 8. Okay, and the 8-bit code for 8 is actually 000 and then 1000. Okay, now because it's doing an AND operation, so we're gonna apply AND and perform that bitwise. And we start with the most significant bit. If you look at this right here, this right here, 10110. Any of the input is 0, the output is going to be 0. Again here, if I move this over here, any of the input is 0, output is going to be 0, and I'm going to keep on doing it 0, 0. First 4 will be 0 because these are zeros. And then if I look at 1, and then I have 1 here, then I also have 1 over here. So I get 1 here, and then I got 3 zeros here, so 0, 0, 0. And if you notice, this actually makes a code of 8. You know, if you look at the third bit, 0, 1, 0 will be 0, and then I got 1, 1, 0, that's again a 0, so I got this 0 right here. And then how I got this one is this, when I do a bitwise operation and on this one, because all the inputs are high, so I get high. Then similarly here, one of the input is 0, so I get 0, and so on. This is how it's working, and you can try this on different operations and different combinations, and you'll see it will work. Okay, let's go back to our project. Hey, it was synthesized completely and successfully. Okay, I'm gonna skip this part. Actually, yeah, I'm skip this part right now. Maybe I can do it. Well, let's just get it for now. Okay. Now, the next part is actually making the constraint file. So I right click here, click add sources, and then create constant, next, create file. So let's say basic. Okay, finish. Here's my file. And actually, if you go to Google and just type Basys 3 constant file, it will appear. This is the first thing will actually get you over here. So I need 10 switches to 0 to 9, and I'll just copy it from here and paste it over here. I just need to remove all the hash signs. And the reason I chose the variable for switch is SW, so I don't have to make all those changes over here. See, it's already SW and in lowercase. Verilog is a case-sensitive language, and you have to make sure that your variable names matches exactly in your constant file. Otherwise, it's gonna throw you an error. Here, I'm just about done. So I got my 10 switches as inputs. Now I need 8 LEDs, so I'll go back here and look for the constant file for LEDs. 0 to 7 here, and then paste it over here. Perfect. Again, my LED is, I got LED all in caps, and here also everything is in caps. LEDs as output. So I got everything done. I'm gonna save my file. I'm gonna click my source file, design file here, and then gonna run implementation. And again, might just take a few minutes before everything is complete, so just be patient. Hey, awesome! Implementation complete. It took a little longer, maybe a couple of minutes, but I got this done. So let's generate the bitstream file, which is our next step. And for that I need to open the hardware manager. I just plugged in my Basys 3 board. Let's click open target. Actually I'll just do it from here. Open target, it should automatically detect, which it did. Let's click on one of those, and hopefully our chip, which is RTX 7 X7835T, which is right here. So awesome. Now we need to program the device. So I click here again. All right. Click program, and the bitstream file has been generated. Okay. All right. If you actually notice here, my green LED, which is right above done, is green. That means the bitstream file has been successfully deployed. Now I'm going to implement, and I'm actually going to verify. I've already implemented, I just need to verify it now. So say I want to do 4 plus 2. Okay, so Alright, so that makes 4. Remember, this is my switch 0, switch 1, switch 2, and switch 3. 0. Now right now it's making code 0, 1, 0, 0. So that's 1, 0, 0, 4. And then this is my switch 5, switch 6, switch 7. Switch 7 right here. Okay, so let me say, I want to go with 2. Okay. Let's do, okay. So that makes 0, 0, 1, 0. So that makes a code of 2. And because switch 8 and switch 9 are set to 0, 0, switch 8 and switch 9 are set to 0, 0, that means it's going to add. So 4 plus 2, 2 plus 4 makes 6. Okay. Say I want to do multiplication, which would mean that switch 9 needs to be 1 and switch 8 needs to be 0, and we know 0, 0, 1, 0, which is 2, and 0, 0, 1, 0, 1, 0, 0, which is 4. 2 times 4 is 8, and if you look at it, it makes a code of 8, 1, 0, 0. Okay. If I want to change the number to from 0, 1, 0, 0 to maybe 0, 1, 1, 0, 6, so that makes a code of, so this makes 0, 1, 1, 0, 1, 1, 0, 6, and then 2 is 6 times 2 is 12, and 12 is 1, 1, 0, 0. If I bring this operation down to 0, 0, that means we are adding, and now we know 6 plus 2 is 8, and that 1, 0, 0. So that's pretty much it, guys. I hope you enjoyed the video. Please do that, and if you have any question, if you get stuck, leave a comment or ask me a question. Thank you for watching. Enjoy your day. Bye.